Welcome to the Cardiac MR Learner Series, a unique video tutorial program under the aegis of Indian Association of Cardiac Imaging. This program is focused on beginners and intermediate images with learning happening through short sessions and case-based discussions. We are grateful to experts from different parts of India who have helped us in putting this program together. Please do feel free to give us your feedback so we can continually improve such training opportunities. This session is brought to you by Dr. Pudhiavan, who is a lead consultant radiologist in cardiothoracic imaging in Kovai Medical Center and Hospital, Coimbatore, Tamil Nadu. He has expertise in adult and congenital cardiac MR and CT with interest in interstitial lung disease. He finished his initial training in Apollo Heart Center, Chennai, and then took up his fellowship in Narayana Institute of Cardiac Sciences and is a level 3 CMR certified radiologist from the European Association of Cardiovascular Imaging. He has 10 publications in national and international journals and has been a part of the organizing committee for a number of CMEs and conference on cardiac imaging.
Hi everyone, welcome to the CMR Learner Series. I am Dr. Pudhiavan, Consultant Cardiothoracic Radiologist at Kovai Medical Center and Hospital, Coimbatore. In this talk, we will cover the basic physics and sequences pertaining to MR in general. The objectives of this talk will be to highlight the steps in MR image formation, the basic concepts of T1 and T2. We will also see about the components of basic pulse sequences, and lastly, the important sequence parameters that we can control to obtain good images. There are 5 basic steps in MR image formation. The first is excitation, relaxation, acquisition, computing, and display. As we all know, human MR imaging is dependent on the hydrogen protons in organic tissue. When a human is placed within the MR gantry, the hydrogen protons align either with or opposite to the external field, with a net moment in the direction of external field, that is along z-axis. When an external RF pulse is applied at the Larmor frequency of the protons absorb the energy and are deflected into the XY plane. This process is called excitation, and the angle by which it is deflected is called the flip angle. Once the RF pulse is stopped, the protons again tend to align themselves along the external magnetic field. Energy is released during this as heat and RF wave. This process is called as relaxation. There are 2 types of relaxation, T1 and T2 relaxation. T1 relaxation, also called spin lattice relaxation, is the exponential recovery of magnetic moment along z-axis. The T1 time is a constant, which is the time taken for the magnetic moment to reach 63% of its original value along the z-axis. The T1 relaxation is a relatively longer process and is different for different tissues. The T2 relaxation, also called spin-spin relaxation, is an independent process to T1 relaxation that happens at the same time. This is different to T1 relaxation and is due to the dephasing of protons in the XY plane. The T2 relaxation is a much shorter process and it consists of 2 components, T2 and T2 star decay. T2 star is the rate of actual dephasing and is quicker than pure T2 relaxation due to the presence of magnetic field inhomogeneities. The T2 time is the time taken for 37% of the protons to have dephased in the free induction decay. So, to make it short, T1 and T2 relaxation are two independent processes that happen simultaneously. T1 relaxation happens along the z-axis, while T2 relaxation happens in the xy plane. These are different for different tissues, and T2 relaxation is a quicker process compared to T1 relaxation. The next step in image formation is acquisition of RF signals using receiver coils. These coils are placed at right angle to the B0 main magnetic field, and the RF pulse induces a current in the receiver coils. And the last steps are computing and display, which consists of analog to digital conversion, Fourier transformation, and K-space filling. I am not going to explain these as they are beyond the scope of this talk. So, to summarize, the MR image we view on a display passes through these complex steps carrying image information. Now that we know the steps of image formation, we shall move on to other issues. Though a RF wave is emitted during relaxation, an image cannot be formed as we don't know exactly from which body part that comes from. To solve this problem, we use something called gradient coils. The gradient coils are located within the gantry and are used to apply additional small magnetic fields in the X, Y, and Z planes. Slew rate is a measure of the power of a gradient coil, which is the maximum power divided by the rise time. The higher the slew rate, more powerful is the gradient coil. The gradient coils are used for encoding the RF signal with 3D positional data to identify from which particular voxel in body tissue that signal comes from. For an axial section, the gradient along the z-axis acts as a slice selection gradient. When this gradient is applied on top of the main magnetic field, it changes the frequency at which the protons precess both along the negative and positive sides. Now, a RF pulse with a particular frequency will excite only that particular slice of tissue that has the same frequency of precision, thereby exciting a thin slice of tissue rather than the whole body. Once a thin slice of tissue is selected using a slice selection gradient, then a phase encoding gradient is applied in the y-axis. This changes the phase at which the protons are precessing along the gradient field, thereby differentiating different lines antero-posteriorly which precess at different phases. The third gradient, which is the frequency encoding gradient, is then applied during the readout of RF signal in x-axis. This causes a subtle change in the frequency of precision of protons along the x-axis, thereby differentiating columns of tissue from right to left. So, finally, after all three gradients are applied, the RF signal will be differentiated into slices and voxels, and each pulse from any single voxel will have a unique frequency and phase, helping in their three-dimensional localization for image formation. The slice, phase, and frequency selective gradients can be applied in any of the planes, giving the MRI the multiplanar capability. A pulse sequence is a sequence of events that is needed to acquire a MR image. This is because immediately after an excitation pulse, the T1 and T2 relaxation and the free induction decay starts immediately, giving us no time for applying the gradients. To overcome this, we use specific techniques called pulse sequences. The first most basic sequence is the spin echo sequence. It consists of a RF pulse, usually a 90 degrees, followed by a 180-degree refocusing pulse, after which an echo or RF signal is produced. The purpose of the 180-degree refocusing pulse in a spin echo sequence is to flip the transverse magnetization in XY plane by 180 degrees so that the protons again come in phase to produce an echo. In a spin echo sequence, the slice selection gradient is applied along with the 90-degree and 180-degree pulses. This is to make sure only a desired slice is excited by the 90-degree and the refocusing 180-degree pulses. The phase selective gradient is applied between these pulses, while the frequency selective gradient or readout gradient is applied during the signal or echo acquisition. The advantages of spin echo sequence is that it has a high signal to noise ratio and is less susceptible to magnetic field inhomogeneities. The disadvantage is that it is time consuming and it also results in high RF deposition because for each signal produced we use two pulses, one 90-degree and one 180-degree pulse. Spin echo sequences consist of three main parameters: the TR or repetition time, TE or time to echo, and flip angle. The TR time is the time interval between one 90-degree pulse and the next 90-degree pulse. The TE or time to echo is the time between the 90-degree pulse and the echo signal. The flip angle is nothing but the angle by which the deflection of the proton happens after the first RF pulse, which is 90 degrees in this case. The next important sequence is the gradient echo sequence. It is different from spin echo sequence in that it does not use a 180-degree refocusing pulse. Instead, after the initial RF pulse, a strong gradient is applied, first positive direction followed by negative direction, with the negative gradient for twice the duration. This results in the formation of an echo signal. The RF pulse in a gradient echo sequence causes dephasing of protons. With the initial positive gradient, there is rapid dephasing. The negative gradient that immediately follows causes rephasing of protons, resulting in an echo signal. Since the gradient echo sequence does not rely on a 180-degree refocusing pulse and much smaller flip angles are possible, the sequence is much faster than a spin echo sequence. The image contrast in these sequences depend on different parameters. In a spin echo sequence, a longer TR and longer TE results in a T2 weighted image, whereas a shorter TR and shorter TE results in T1 weighted image. A longer TR and a shorter TE in a spin echo sequence results in proton density weightage. Whereas in gradient echo sequences, the image contrast is dependent on the flip angle and TE time. A larger flip angle and shorter TE results in T1 weightage, whereas a smaller flip angle and longer TE results in T2 weightage in a gradient echo sequence. The IR or inversion recovery sequence is a specialized spin echo sequence. Here, in addition to the normal 90-degree and 180-degree pulses that are used in spin echo sequence, another inversion 180-degree pulse is used before the 90-degree RF pulse. The 180-degree inversion pulse in a IR sequence results in a 180-degree inversion of the magnetization into negative side of z-axis. This is followed by regaining of the magnetization from the negative to positive side of z-axis in the protons. This rate of regaining magnetization is a constant and is different for different tissues. So, if the 90-degree RF pulse is applied exactly at the point the magnetization of the proton of a tissue passes through zero, then no signal is produced from that tissue, resulting in its suppression. The Ti time is the interval between the 180-degree inversion pulse and the 90-degree RF pulse. So, a stir sequence uses a short Ti time so that signal from fat is suppressed, while the flare sequence uses a long Ti time and hence signal from CSF is suppressed in that sequence. There are certain parameters in each of these sequences which can be modified to change the image contrast, image quality, and imaging time. An increase in TR causes a reduction in T1 contrast with an increase in PD contrast. An increase in TR also causes an increase in scan time, whereas an increase in TE will result in an increase in T2 contrast. The larger the flip angle, more will be the T1 contrast and more will be the amount of signal that is acquired. A change in Ti time will result in suppression of different tissues depending on the tissue to be suppressed. The Na, or the number of acquisitions or excitations, is the amount of signal that is reacquired from a single voxel. So an increase in the number of acquisitions results in more signal and less noise. However, this results in artifacts if there is movement between the acquisitions, and this also results in an increase in the acquisition time. An increase in the matrix size, keeping the FOV constant, will result in the reduction of size of a voxel. This causes a reduced signal, low signal to noise ratio with high spatial resolution. The scan time is also increased. A larger FOV with constant matrix size will result in high SNR and low spatial resolution. The slice thickness, if increased, will increase the signal and coverage at the expense of spatial resolution, and there is increased chances of partial volume effects. Slice gap, when reduced, increases the chances of crosstalk between slices, which is nothing but wrong excitation of undesired areas out of the slice. Phase wrap is a phenomenon which happens along the phase encoding direction when the FOV is small. This results in overlapping of tissue image from out of the field of view. This can be overcome by either increasing the FOV or using phase oversampling in the phase encoding direction. Before I wrap this talk on basic MR physics, I will just outline some of the common sequences used specifically in cardiac MR. We shall go through their details and how to optimize them for better image quality in my next talk in the series. The routine black blood image obtained are basically spin echo images, while the white blood images are obtained from gradient echo sequences. The CNE images use a balanced steady-state free precision or a spoiled gradient echo sequence. The ECG-triggered T1 and T2 black blood images are obtained by a double inversion turbospin echo sequence, while the STIR images use a triple inversion recovery turbospin echo sequence. The dynamic perfusion sequence used for perfusion imaging uses a hybrid EPI technique most of the times. The delayed enhancement images are obtained using a fast gradient echo sequence with phase-sensitive inversion recovery. The flow images use a phase contrast for velocity and volume data. Lastly, the T1, T2 mapping and T2 star images are parametric pixel level mapping techniques which are dealt with in separate talks. To conclude this talk, a basic understanding of MR physics will help us in obtaining good quality images. At the same time, we need not get overwhelmed with physics as we are not physicists here. Most modern CMR sequences use a heavy improvisation of the spin echo and gradient echo sequences, and MR physics will require multiple reads and it should be given the time it deserves. I thank you all for patiently listening through this complex subject, and please feel free to give your feedback in the comment section. Thank you.